Hi everyone. So in this lecture, we're going to start module 9, and this is going to bring us outside the textbook because the textbook doesn't actually do these kind of very, well, at least to me, very interesting little circuits that you can build with digital electronics, such as adders and multipliers. Um, so when I was a kid, the first, real electronics device I got, well, actually, the first one, no, I'm sure I got a calculator before I got a radio. Yeah, so the first electronics device I ever had that was mine was a calculator. And the thing I probably did to it, I probably took it apart and tried to figure out how does it actually add. And of course, even back then, these are still integrated devices. And then when you open it up, you just see a bunch of chips and like there was no way for me to figure out how it actually adds. And now we get to figure out how does a computer actually add, not just a calculator, but anything that uses digital computation. What is the methods used in order for us to add numbers together in this case? So we're going to start off with some half adders. This is actually what's not is not used because it's not as scalable as full adders. So, but this really demonstrates the logic of adders very, very well. Because you basically can just take what you learned from elementary school, how you add, and then implement it as on a circuit with logic gates. And you can see that it's the same exact mathematical logic that goes into electronics logic. Okay, so let's review how we add on paper before we try to do it on a breadboard. Okay, so let's say I'm trying to add the number 1, just keeping things simple, and to 3. So I'm going to write these in 4-bit um, sign integers. So this is the ones place, this is the twos place, this is the fours place. The smallest number you can represent is -7. The biggest number you can represent is +7. Because remember that first bit is actually the sign. It tells you whether something is positive or negative. Okay. So in binary, right, 1 is just 0, 0, 0, 1. 3 is 0, 0, 1, 1. And then just as you learned in elementary school, when you want to add two numbers together, you line them up like this, right? Okay, you save a little space up there for the carry. Put a little plus sign here, right? When you add 1 plus 1, you get a 0 with a carry of 1. Okay, right? Just like if you add 5 plus 5 in decimal, right? You get 10, but then you write 0 with a carry of 1 on the next place, okay? Because this is the next place, okay? So 1 plus 0 plus 1 gives you a 0 with a carry of 1 once again, okay? 1 plus 0 plus 0 gives you a 1. 0 plus 0 gives you a 0, of course. And hopefully this is equal to 4 in decimal, right? This is the ones place, twos place, fours place. So 4 times 1 gives you 4. Okay. Well, so and let's do this for a negative number just in case that, with this, do we have to do a different logic for negative number? We'll see. Okay. So -1, right? So just -1 plus 3 or 3 minus 1, right? So that's basically the same thing as doing this. Okay. So let's put the 3 on top. Okay. So 0, 0, 1, 1, and then -1 in 2's complement, right, is 1, 1, 1, 1. Actually, lots of ones. Okay. And then since you're adding a positive and a negative number, which is subtraction, right? You're still adding. So 1 plus 1 gives you a 0 with a carry of 1. 1 plus 1 plus 1 gives you a 1 with a carry of 1, right? Because that overflows over. 1 plus 0 plus 1 gives you a 0 with a carry of 1. 1 plus 0 plus 1 gives you a 0 with a carry of 1 over here, but you just ignore that because it's gonna overflows over the bits. Okay. All right. Hopefully this is 2, and this is indeed 2 in decimal. So one thing you notice is that, right, when I do the first step here, right, 1, 1, right? That's a 0 if we have an exclusive OR gate, right? Right. The output here from this step going down like this, right? So if one of them is 1, right, you'll get a 1 here. If the second one is 1, you get a 1 here. If both of them are 0, you get 0. Both of them are 1s, you get 0 still. So this is a exclusive OR operation, right? Then the place to go to the carry, right? Only when both inputs are 1s, you get a carry of 1, right? So this is actually an AND operation, okay? So let's see how this turns into electronics, okay? So it seems like we want, you know, these bits to go into some sort of exclusive OR gate and a AND gate, okay? So this circuit is known as a half adder, okay? So get rid of the little selection thing, right? So A here is this row input, and B here is the second input. So A and B represent two different sets of numbers. And in fact, in the future, when we have to do multiple bits, this will be A0, B0, represented the lowest significant bit, meaning the ones place bit. Okay. And what happens is that you put this into an exclusive OR gate. Oops. Well, let me do the little thing here. Right, XOR. And sorry, and you put these input into another gate, the AND gate, at the same time. Okay, the exclusive OR gate gives you this number. Oops, right, gives you this number, right? The AND gate gives you whether or not there's a carry that's going to be carried over to the next place or not. Okay, so this is like a very simple, right? 2 gates allows you to add 2 1-bit numbers together. Okay, so this is the physical diagram, and then what happened is that these diagrams gets more and more complicated because you're gonna not adding 1 bit to 1 bit all the time, right? You may want to add 50 bits to 50 bits sometimes, or 64 bits in all our computers these days, right? So this turns it into so the way people simplify this is to basically change this to a functional diagram. Okay, so no longer it doesn't draw the gates inside there anymore, but it just shows you, oh, this is a half adder, and this is the function where it takes 2 inputs and gives you 2 outputs. Okay. Okay. So this is known as a half adder, okay, because we actually, if we have to add 2 bits, you don't just put 2 of these together, you actually have to put 3. So the half adder is a little bit misnomer, but it's like a 2/3 adder, let's say. Okay, and we're going to see how this grows. Okay, so let's do an example where we're doing 2 bits. Okay, all right. So remember when we're doing 2 bits, right? Let's say we're doing 3 plus 3 equal to 6, right? So let's put the zeros in here also. Okay. So 1 plus 1, you know, give you 0 with a carry of 1, right? And then 1 plus 1 plus 1 gives you a 1 with a carry of 1, and then you have the 1 at the end here, and this will be 4 plus 2 right at the end. That gives you the number 6. Okay, so how do we do this when we have to put this into a circuit? Okay, so I'm going to do this with the full schematic for this time, but you're going to see how this becomes a little untenable when we start making it too many bits. Okay, I'm going to do A0, B0 here, and then for the second bit, right, in the 2's place, I'm going to put, oops, A1 and B1, not B2. I'll do that. Okay. In fact, I'm going to give myself a little bit more space. So yeah, so I have enough space here. A1, B1. Okay, so A0, B0 goes into the exclusive OR gate, as you expect, and the output gives you, let's call the output Q, right? That gives you the least bit, right? So if we can highlight these things, so this is actually the same as this, right? And then this number is the same as this one. Now the color, this number is this one, right? So this is the A row, right? Which is a vector, right, of stuff. And then the B row, which is a list of numbers, binary numbers, okay? And then the Q's are down here, right? They actually use Q. Oh, they use O for output. I don't like that. Let's just use Q, okay? Okay, because O's looks like zeros. Okay, so but remember, right? Not only do we want this in the exclusive OR gate, so we also want it to go through an AND gate. So I'm gonna put a little dot here. So a dot here represent that I make the connection, where if I don't draw a dot, it means it's not connected. Okay. So I'm gonna put a little dot here for B, and I put it in here. Okay. And this is going to go to not the output directly. This is going to be the carry bit. Okay. Let's see what they denote that as. Yeah, they denote that as C. Okay. Actually, I like what they denote up here. L. Let's just put L here instead of Q's. Okay. So all the Q's becomes L's. Okay. And this is the carry bit for the 0th place. Okay. And that's going to have to go somewhere else, right? Because you're going to be adding these into other parts. Okay. Okay. So before we go on to the next stage of the cascade, let's just do the same thing for the 2's place, which is 2 to the 1 power, right? Because it's binary. So the A1 and B1. Okay. So we're going to do the same thing here. We're going to have an exclusive OR gate, and then the A just goes in, and I draw that very badly. Things don't even line up. Okay. So exclusive OR, right? And then you have an AND gate on the bottom here. Then you tie A together, you tie B together. Okay. And once again, this will go into another thing. We're going to see what that is. Okay. And then this AND gate here is going to be C1. Okay. And we're going to see where that goes. Okay. So in order to get the right result, what we need to do is actually pipe these two into a second set of half adder. Let's not make this too long. I'll run out of space. Okay. Okay. And a half adder, right, is basically an XOR gate with an AND gate. Okay. Okay. Right. And this second, well, this third, but it's like a level 2 XOR gate, right? That's going to tell us the output for the 2's place bit. Okay. Okay. And this carry over here, right, will have to come out, and this output here does not get to go straight out. Okay. It's going to have to go through a regular OR gate, not an exclusive OR, just a regular OR, so it doesn't have the second little parentheses there. And that's actually going to be the third bit, okay? The 2 to the second power bit, so it has the value of 4. Okay, so let's see if this works. Okay, so a little diagram up here, right? I'm gonna highlight some stuff. Oops. Erase. Right, I'm not gonna erase the little bit parts. Okay, all right. Let's see, make sure this works. Okay, so so this is the 0th bit, the 1's bit, the 2 to the 2 powers bit. Okay, so let's just double check that we do get the right answer, at least in this case. Okay, so So in this case, right, so A and B are these, right? And then we're dealing with the 0th column here. Okay, so that's 1, 1. So exclusive OR of 1, 1. This should have an output of, let's do that in green, of 0, right? Because if only one of the inputs is high, you get a output of high on an exclusive OR gate. But the AND gate here gives you a 1, right? So 1, 1 AND gives you a 1, right? Let's deal with the other inputs, which is these two guys, right? So once again, those are still 1s. So the outputs here are actually the same. You have 0 for the out of your, in fact, what I'm going to do is write the 0 here so we kind of go step by step. Okay. Okay. And then the output for the AND gate is 1, of course, because we have the same inputs. Okay. Now, right, this goes into a second, right, exclusive OR gate, right? And then since only one of the input is 1, you actually have 1 as the output here. This just gets passed along as a wire, so there's actually no logic you need to do. We'll just keep going, right? So far the answer is 0, 1. So check that. And hopefully this L2 is also 1. So let's see what happens. Okay. And here, right, so these outputs from the first layer of gates, right, is 1, 0. Not only does it go to the XOR gate, it also goes to the AND gate. But the AND of 1, 0 is actually 0, right, because you need both of the inputs to be 1. Okay, and this output from this AND gate just gets passed along here, right? And now this OR gate, right, has an input of 0, 1, and an OR of 0, 1 gives you 1. So the answer is indeed correct, at least in this case. And then maybe in the pre-lab, we'll do some exercises to double check this. Okay, so hopefully I drew the same diagram as what's up here. Yeah, so the book drew the functional diagram for you, where I drew the actual gate that's inside each of these functional diagrams. So, this functional diagram represents these two gates, right? This functional diagram represents these two gates, right? And then, which color do I have left? Green, right? And these two gates is represented by this functional diagram. And you always have a one tie off OR gate at the end in order to do that last bit. Okay, right, so that's how you can do 2-bit adding. I'm just going to draw the 3-bit version of it, but not the, I'm going to draw the functional diagram version of it as opposed to the gate version of it, the actual schematic, right? So the way you do 3 bits is you'd have 3 layers of these things. Okay, so you have A0, B0, A1, B1. Okay, remember inside each of these functional blocks are 2 gates, right? An XOR gate and a AND gate. A2, B2, okay? And the output of this goes straight to the least significant bit. But what we do is we put other half adders in between. You're kind of forming a little Pascal triangle here, okay? And the output of this goes here, the output of this one goes here, the output of this one goes here, output of this one goes here, and this goes almost all the way at the end. It's going to go to an OR gate here, okay? And that's going to give us L3 actually, okay? But the output of this don't just go straight to the output. You have another one until, right, you get to the point where you only have one half adder at the end, and the output of that one half adder goes to, let me do this right. Oh no, I didn't do that right. Up here, right. The output of this half adder goes straight here, right? And let's double check. 3. So that's, why is there an extra bit that I lost. Oh, okay. So so the this last OR gate, it has to take 3 inputs instead. So it's a 3 input OR gate. Okay. So this is a OR gate, 3 inputs for this case. Okay, and this will give you L2. Okay, and these are the bits you actually get. So when you add 2 3-bits number together, you get a 4-bit number, possibly, if the okay. And then the book has the 4-bit version drawn for you, so you can see that this triangle just kind of keep growing, and this OR gate has to be bigger and bigger and bigger every time the output changes. Okay, so if you don't like the O's here, you can just change these to L's. Okay. Okay, so this works very well, right? Because basically what we did is we look at how we add in elementary school, right? And then you implement it on a breadboard, which is a lot of fun. Okay, so let's count how many half adders needed in order for us to, let's say, add n bits of numbers together. Okay, so you can see the pattern here, right? So if you do 4 bits, you need 4 here, 3, 2, 1, well, plus an OR gate. Okay, so in order to do that, right, so n number of bits, right, is n, and then you have to add n minus 1, n minus 2, until you get to 1. Okay, right, until you get to the final 1 half adder gate. Okay, let's erase that. So I pointed to the wrong thing anyway. Okay, and this series, if you looked up what the series is actually n squared minus, well, the sum of m equals to 1 to n minus 1 over m. So this term is proportional to n, oops, little n. Okay, little n is the number of bits, and big N is the number of half adders. Okay, let's just have those definition correct. So the second term is proportional to little n. The first term is proportional n squared. So when n is small, right, n squared and n are still competitive with each other. For example, if you had put a 2 there, right, so n squared, 2 squared is going to be 4, and then minus 2 is going to be 2. Okay, and I think there's actually a plus 1 here also. Okay, because of that additional one final gate at the end. So in order to do 2-bit plus 2-bit addition, you need 3 gates. Okay, but if you have 64 bits, 64 square minus 64 is basically 64 square, right? So you're gonna have a lot of gates in order to do addition for 64-bit. Okay, but this implementation is very simple, very logical, and it's very good for learning. But none of your calculator is going to use this because it is not as scalable. Meaning, as you grow in number of bits, it gets more and more inefficient in computing more bits. Okay, this is why we're going to use a full adder. A full adder is more complicated. It's basically 2 half adder placed together, and initially you would think, oh, that's not going to make it more efficient, right? But those 2 full half adder placed together, what that does is that it makes it so that the number of gates you need per bit scales linearly and is supposed to square, right? So because this n squared is what's killing us, right, when we get to 64. In fact, I think anything above 4 bits or above, is fewer gates to build full adders as opposed to half adders. So we can play around with the math of that. Okay, so the full adder circuit is basically 2 half adder circuits squished together. So you have an XOR gate, an AND gate, XOR gate, and AND gate, and then of course you have the regular AND gate at the end. Okay, so the functional diagram for this, right, is a add instead of a 1 half add. So it takes 3 different inputs. Okay, so it can have a carry in also. Okay, and it has two outputs. Okay, so these are the inputs, these are the outputs. Okay, so let's see, right? So this is the truth table. I think I just kind of copy and paste this out of the book. So when you have 0 plus 0 plus 0, right, your carry is 0, your output bit is 0, right? When you have 1 0 0, right, your output has to be this, and then your carry has to be 0. Same here. But when there's more than one bit, like 1 1, right, you want your carry to be 0, right, and your output to be your that power, that place output to be 0. Okay, so let's check a couple of these. I'm not going to do all what is it, 16 different ones, right? No, 8 different ones. Why there's an A there. Okay, cool. All right, so let's check, make sure that let's do the first row, right, the simplest one. So let's say if I have 0 0 0 as the input. Okay, let's go up here, erase this. Okay, let's do that in red. 0 0 0. Okay, so the input goes into this XOR gate. The output of 0 0 on XOR is 0. The output of a AND gate is also 0, and this 0 gets carried over here also. Okay, and now we're at the second XOR gate, right? 0 0 XOR is still 0, and of 0 0 is still 0, or a regular OR of 0 0 is still 0. You get 0 0. Okay, so that checks out. Okay, nice. Let's do one that has a carry. Let's do 1 1. Okay, so I'm going to erase these two guys and make them into ones. Okay. Okay. Exclusive. Well, the carry is still 0. Exclusive OR of 1 1 is still 0. The AND of 1 1 is 1 now. Okay, so that's the only thing that changed. Okay, see, these are still 0 up here on top. Okay, hopefully you can see that, right? But then the only difference is that you go into this OR gate with 0 1 instead of 0 0, and that changes this output to be 1. Okay, and that exactly checks out. Let's just do one more where we have both, right? Let's do 1 1 1. So change this out input here to be 1. Okay, so that means this turns into 1 also. Okay, the exclusive OR of 1 1 is still 0. The AND of 1 1 is still 1. Now they're having exclusive OR of 1 0, which turns it into 1. Okay, the AND of 1 0 is still 0, so that carries along. Okay, so the only thing that changed here is 1. Okay, so you get 1 1 at the output instead, which is exactly what checks out here. Okay. All right, so that's the fundamental of a single full adder, which allows you to add one bit of number at a time. If you want to add more bits, what you do is you chain multiple full adders together. Okay, so this is one full adder, this is the second full adder, and then for whatever reason the book started counting from 1, but that's fine. Okay, so this carry in here is going to be important because you want to know what the carry in is, right? Because this is going to be 0, so you tie basically the first carry in to ground. Okay, because you don't expect some random number to connect to it. Okay, right, and then the carry out for the first bit goes to the carry in of the second bit. The carry out of the second bit goes into the carry in. Carry out of the second bit goes into the carry in for the third bit. Okay, and the outputs, of course, goes to each consecutive bit. So notice once again, right, this is 4 bits plus 4 bits, right? That gives you a 5-bit number at the most. Okay, so the biggest number you can have is 15 plus 15, which is, you add them together, is 30. The biggest number a 5-bit number can hold is 31, right? So it's still within the limit. So each of the full adder costs twice as much because you basically double the number of XOR gates and AND gates in each adder. But the scaling of this full adder, instead of being scaled as n squared minus n, you actually just scales as n, which is nice, right? So if we do an example where we're doing a 4-bit addition using half adders, right? That needs 10 half adders because of the 4 plus 3 plus 2 plus 1, okay? Plus an XOR, plus a regular OR gate, okay? So if you break the half adders into their components, right, that's 10 XOR, 10 AND gates, and 3 OR gates, a 3 input OR. You have to have 3 OR gates, or a 4 input OR gate, basically. Okay, that's 23 gates. If you build a adder out of full adders instead, same number of bits, okay, each of the adder has more parts in it, right? You need 2 XOR gates and 2 AND gate and 1 OR gate per full adder, but you only need 4 of them because number of bits equals the number of full adders you need. Okay, so 4 times 5, there's 5 gates inside each full adder. That's only 20 gates. You already saved 3 gates by going to 4 bits. So if you want to add anything more than 15 plus, well, anything more than 7 plus 7, the full adder is actually more efficient compared to the half adders. Okay, so going back to the full adder circuit above, I just want to kind of count up the number of wires in order to build one of these things, and you will experience this next week in lab. Okay, you count up the wires. There's actually 13 wires in each of these full adders. Okay, it's like 13 wires. Oh, okay. I'm good. You got a 3-hour lab. I can handle it, right? But that's just to add a 1-bit number together, right? So let's say you want to add 64 bits together. Okay. Not only do you need to wire the logic input and output between all these gates, but you also have to power a lot of these gates, right? Because every 4 gates requires a power, a VCC and a ground. Okay, so that's 2 additional wire for every 4 gates. Okay, and there's actually 3 different type of gates, right? You have an XOR, an AND, and an OR. And in fact, you may even need more because we don't have some of these gates in stock, so you have to make them out of NAND gates or NOR gates because those are the universal gates. And so each gate could take 19 or more wires in order to wire up. Okay, and then if you take 19 times 64, because you need to build 64 of these, that's about 1,200 wires. Hopefully, you never have to do that in the real life. That'll be kind of an interesting summer project to do if you really want to do it. Okay. So this is why we're going to move on to something called the field programmable gate array in this lab. That way you can add numbers that are actually substantial as opposed to just adding, 3 plus 3 all the time. Okay. But this circuit works really fast. So one thing that's really, really important is that once this is wired up, right, basically when you change the input of Cn, A, and B, the output changes instantaneously. It's not one step at a time, right? Right. It may seem like, oh, you have to go through this first OR gate first, and this first XOR gate first, this AND gate first. But no, right? Because this input goes directly to the second XOR gate. So naming these first and second is actually kind of a misnomer. So all the wires are in place. Basically, the information gets propagated through these gates at the speed of light, and then you'll get an output without any delay at all. Okay, so there's no delay between the input, but almost no delay. Basically, the speed of light divided by the length of your wire. That's the wait. Is that no? It's the length of the wire divided by the speed of light. That's the delay you're getting. Okay, so we're talking about stuff that are less than a nanosecond. That's, and this works really fast. And in fact, a lot of these days, instead of building field programmable gate arrays or circuits like this, what you can do is basically, build the circuit on a breadboard and shrink it down into something that's the size of a chip, so an integrated circuit, right? And these are actually known as application-specific standard products. So you can just build a 64-bit adder, and then it just has 64 inputs, and it gives you 65 outputs. Sorry, not 64. 64 times 2, so 128 inputs and 65 outputs, and it just adds like in a flash, okay, in a nanosecond can add, okay. All right, so that's all for this lecture. So next one we're going to do some multiplication, and then I'll introduce you to other techniques that we can use to do more complicated circuits.